All right, it's time to expand on some previous discussions we've had. We've been talking about work and energy, and I want to take a look at a couple of different amounts of work done by forces. And we're going to start off with work done by gravitational force. So let's assume I've got an object here, and I'm going to tell you this object has a mass of 1 kilogram. Doesn't matter if that's correct or not, but 1 kilogram. To make my life simple and say that G is equal to 10 meters per second squared, or 10 meters per second. 9.8 is the actual value here near the surface of the Earth, but 10 is just easier to work with. So mg is equal to 10 newtons. So the gravitational force is down with a value of 10 newtons. All right, so what I'm going to do is I'm going to move the object from position A to position B. So here it is at position A. I move it up to position B. That distance is 3 meters. Of course, not really, but that's okay. So we're going to assume that that's 3 meters. So I move it up from position A to position B. How much work is done by gravity? So the work is equal to force times displacement, right? So I'm going to say U from A to B, that's equal to mg dotted with, in this case, delta y, right? Those are vector quantities. Mg is down, right? That's 10 newtons down. 10 newtons in the negative j direction, dotted with 3 meters in the positive j direction. So the net work done by gravity, let me rephrase that, the work done by gravity is negative 30 newton meters, or negative 30 joules. Right? So negative 30 joules. That's how much work is done by gravity when I go from A to B. Now, I'm also applying a force as I go up, but we're not going to worry about that. We're only interested in the force done by gravity. Then as I go from B to C, I'm traveling a distance of 4 meters. Okay, again, the work going from B to C, that's going to equal negative 10 newtons. J, that's the force due to gravity, and I'm interested in the work done by gravity. And I got that with 4 meters in the I hat direction. So J dot I is 0 because they're at 90 degrees. So the work done going from B to C is equal to 0. All right? So work done by gravity going from B to C is equal to 0. All right, then the object's going to move from C down to D, right? Pretty much the same equation that I had over here, except that the delta y is going to be negative 3 meters, okay? So the work going from C to B, that's going to equal negative 10 newtons. 10 newtons J hat dotted with negative 3 meters J hat. And so I'm going to get positive 30 joules. So the work done by gravity coming down from C to D is positive 30 joules. Finally, I'm going to travel from D back to A. When I travel from D back to A, the work is going to be 0 again, because it's going to be negative 10 newtons, negative 4 meters, but in the I direction. J dot I get 0. All right, so the work done by gravity going from A to B to C to D to A again is 0. The net work done by gravity is 0. Let's do one more path. Let's do the path from B to D, right? The path from B to D. So I'm going to move the object from B over here to D, okay? And when I do that, the work done from B to D, the work done by gravity, is going to equal negative 10 newtons in the J hat direction, dotted with, this is a vector quantity, this is going to be 4I minus 3J. 4I minus 3J meters. And when I do the dot product with J dot I, that's 0, right? That's going to go away. And then J dot J, I'm going to end up with negative 30 joules. Negative 30 joules. Or I could look at it this way. My displacement is 5 meters in this direction. And then my force is 10 newtons in that direction. And it's force times distance. Remember, it's dot product. Force times distance times the cosine of the angle in between. Well, here's the angle in between. And the cosine of that angle, well, it's the same as this angle right here. The cosine of that angle is 3 meters over 5 meters, or 3/5. So I'm going to get 10 newtons, 5 meters times 3/5, and that's going to equal 30 joules. And this should be positive, not negative, right? That should be positive because the displacement is down, the force is down. So 30 joules. So if I go from A to B to D to A, I'm going to get 30 joules, negative 30 joules, positive 30 joules, and 0 joules. And so I end up with 0 joules. So when I make a circular path, not necessarily circular, in this case it's all rectangles and triangles, when I make a closed path, when I go from A to some other point, back to A again, the work done by gravity is 0. Right? Now the work I'm doing might not be 0, but the work done by gravity is 0. And when the work done by gravity in a closed loop is 0, we call that a conservative force. Okay, that's called a conservative force. And in calculus, the way we do that is the work done by a conservative force is equal to the integral, and it's a closed integral, so you'll learn this in probably your 3rd semester of calculus, a closed integral of f dotted with dr. So this is a more generic format. I've done very strict, triangle or rectangular paths, but in general, the work done by gravity in a closed loop is going to be 0. And there are other conservative forces. Springs are conservative forces, for example. Okay, so the net work around a closed path by a spring will be 0. I'm not going to go into that one at this point, but there it is for gravity. Now, what would be a non-conservative force? Well, let's assume that I'm dragging this along the board. Right? I'm going to drag it along the board, and when I do that, I have a frictional force, and I'm going to stipulate the frictional force as 5 newtons. Doesn't matter what it is exactly. So I slide this along the board from A to B. Right? I slide it along the board from A to B. Well, that means that the frictional force is 5 newtons down, but the displacement is 3 meters up. So they're in the opposite direction. And so that's going to be negative 15 joules. So the work done by friction is equal to negative 15 joules. Okay, that's moving it from A to B. I didn't subscript that there, and I guess I can. Let me just put A to B. All right, so the work done by friction from A to B is negative 15 joules. Now when I drag it, right, I'm sliding it along in this direction. I won't actually slide it or I'll erase everything. When I slide it from B to C, there's 5 joules in this direction. And there's 4 meters in that direction. 5 joules, 4 meters in the opposite direction. So I'm going to get negative 20 joules. So the work done by friction from B to C is negative 20 joules. Right? Negative 20 joules. All right, real briefly, when I go from C to D, I'm going to get negative 15 joules. Right? My displacement is 3 meters in that direction. My force is 15 newtons in that direction. Not 15, 5. And so the work done by friction from C to D is equal to negative 15 joules. And then finally going across this way, I'm dragging it to the left. The force is 5 newtons in that direction, 4 meters in that direction. So the work done by friction going from D back to A, negative 20 joules. And so when I add up all of those works done by friction, negative 15, negative 20, that's negative 35, negative 15, that's negative 45, negative 50, and then negative 20, I get negative 70 joules. I don't get 0. Right? I don't get 0. So friction did not give me a 0 in this closed integral. I need to put that down. If it's a conservative force, the net work is 0. Friction is not a conservative force because when I went around, it didn't end up being 0 for the net work done. So friction is not a conservative force. Gravity is. Springs will be conservative forces as well, and there are many others. Electrostatic, gravity through space, which is not just mg, it's gmm over r squared, and magnetic forces, those will also be conservative. So there's lots of other forces that are conservative. Friction is not one of them, right? Okay, if you have any questions on conservative forces, leave them in the comments and I'll get back to you as soon as I can. Thank you.